Okay, cool. So I guess we have started. Okay, so probably my screen is visible, right? Just a quick confirm.
Yes.
Yep. Okay, so today we will be looking into couple of things in graph. Okay, and it would be our last session for graphs. Okay, so the agenda would be that we will be going through something as DSU. Okay, which is a very powerful tool in graphs. Okay, and it comes handy in few of the problems. Okay, the last problem which I have solved in DSU on lead code contest is with Deva. Okay, I am not sure whether he remembers or not, but yeah, I solved the last problem with him itself. Okay, on one of the Sundays contest. I remember that problem. Okay, uh, then we will be looking at something as MST, okay, which is minimum spanning tree. We will look into there are a couple of algorithms, but I will discuss only one because that makes our job done for MST. Okay, and at the last we will discuss something as SCC, where we will see a beautiful problem on SCC. Okay, and there is a very famous algorithm which is Kosaraju's, so we will go through that too. Okay, so this will be the agenda, and if time permits, maybe we can take couple of problems from graphs. Okay, so uh, just to give you a note, okay, there is one another famous thing which is Tarjan's algorithm. Okay, so I'm not teaching that right now because I believe like if you cover this and the previous things, if you are becoming perfect on that, then you have to go to Targents. Okay, so that's the reason I'm just stopping till here. But there is one more thing which is Targents, which will help you to kind of find bridges and all. Okay, so it comes into a little advanced concept, but again, if you are familiar with this, even probably at your interest, you can search by yourself and do it. Okay. In case not, if we can find any free time in the later days, we can take it up. Okay. So without further ado, let's start with DSU. Okay. So uh, like as usual, do anyone know about DSU? Did anyone heard of on this term? What is disjoint set union?
Yesterday I saw full form. That's it. Disjoint set. That's it.
So you have seen the full from.
I just saw the full form. That's it.
So what was the use of seeing the full from? No use, right? Instead, you could have solved a problem that would be much better. And okay, I don't want to drag this into session. Okay, okay. So now, what's DSU? Okay, so let's take an inspirational problem and let's see how DSU helps us to do all this kind of stuff. Okay, so the major thing is DSU helps you to find this. There is a very uh, famous problem of like connecting two graphs and finding something like that. Okay, so the inspiration problem would be, let's say you have some graphs. Okay, and initially everyone are kind of disconnected with each other. Okay, and remember this is a single graph, there are 5 components here. Okay, now what I'll be asking you is like every time I will ask you to merge two nodes. Okay, let's say this is node number 1, this is node number 2, this is 3, this is 0, this is 4, and I'll ask you that please merge 2 and 3. Okay, as soon as you merge 2 and 3, you see that the number of components get decreases, right? Now how many components are there in this graph now?
4.
Four.
So there are 4 components, right? Now again I will ask you that go ahead and merge 1 2. So as soon as you merge, maybe I will ask you now how many number of components are there, you will report me 3. Correct? Now again, if I ask you that attach 1 and 3, now how many components are available?
Still.
It's still 3, right? So what I'll be asking you is I'll be throwing you number of queries. In each query, I'll give you two nodes. You have to join them, and at randomly, I will just ask you that, okay, how many components are available. So you have to report how many components are currently available in the graph. Okay. So this is a kind of inspiration problem for this. Now, how will you do brute force? So can anyone let me know?
Like iterating through the
Mm-hmm.
given query,
Iterate. Okay. Mm-hmm.
and we can add to that adjacency list.
Okay.
And later we can find the number of components.
Okay, cool. So yeah, so what would be the time complexity size for that?
For each query, right? Q into big of v plus e.
Exactly. That's cool. Okay. So in order to find, so see, there are two kind of queries, right? One is adding an edge. Adding an edge is a constant operation, but let's say majorly you are being asked to find number of components, right? So what you do is you will do is DFS from each of them and kind of find number of components, right? So that does make sense, right? And like for each query, if you do a DFS, then we are done with the problem, right? But what's the problem? The problem is q can again be up to 10 power 5, and since v and e can also be up to 10 power 5, it obviously gives clearly, right? So we cannot go with our brute force approach. Now let's see how DSU kind of helps us in this kind of setup. Okay. So in DSU we majorly have two powerful methods. Okay, one is find of x, another is merge of x comma y. Okay, so these are the two methods or two functions available in DSU. Okay, and going forward it's all about tweaking merge itself. Okay, whenever you are solving any DSU problem, it's all about tweaking merge code. That's all. Okay, and you would be kind of done with the problem. Okay, so let's start with find x. Okay, what's find x? So you remember, right? The initial problem statement was you were given some kind of disconnected nodes, right? This was the initial setup, and there were some numbers, let's say 0, 1, 3, 2. What we start is whenever we merge, okay, whenever we merge, what we do is we kind of create like a tree structure, okay? That is, one is connected with zero now, okay? One is connected with zero. Let's say now I'm asking you to connect 2 and 3. Okay, so you might arbitrarily choose something, I mean any of them as a parent, okay, and connect. Let's say 3 is the parent now. Okay, now when you connect, let's say again I ask you that please connect 1 and 3. Okay, please connect 1 and 3. So what you do is you kind of like do something like this. Okay, not exactly like this, I will explain you going forward, but just for the simple explanation, I'm just I have taken 3 attached to 1. Okay. Now, what does find of x means? Okay. So, can you see this is some kind of a tree structure formed, right? This is a kind of tree structure being formed, right? So, at any instant, if you say find of 3, so the find of 3 should give you the root, always the root, or this is even known as representative or kind of root node. Okay, so if you ask anything, let's say even 2, 3, 1, or even 0, because it will be something like this. Okay, anything if you ask in this component, okay, if you ask find of 3, it should return you 0. Why 0? Because 0 is kind of the representative or the root. Okay, so is it clear? Is the find x clear? I mean, I'm not asking any kind of implementation. Is the theory clear? That's all. I just need that.
Yeah.
Okay.
So in that
Yes.
in the tree, if we give any input, it should return the root value, right?
Exactly. So find of anything should give you the root or the representative. Okay.
Okay.
Cool. Is it okay, Sas?
Yeah, yeah, got it.
Got it. Chalo. Okay. So next thing, this is a kind of theory of I mean what for the find. So find of 3 should return you 0. Find of 1 should return you 0. Find of 2 should return you 0. Find of 0 should return you 0. Okay. Now, whatever the links you see, these are nothing but these are parents. Okay. Key 1 is a parent of 3. 3 is a parent of 2. 0 is a parent of 1. Similar to a tree structure. Okay. Obviously, we will not be forming with our bait things. I mean, DSU will take care of all this, but just to as a theoretical perspective, this is what it gets formed. Okay. Now, so we have seen regarding the find. Okay, let's see what about merge, right? So what does this says? Merge of x comma y. Now, as the name suggests that you have to kind of take two nodes and kind of join them. Okay, so let's say we kind of formed maybe two trees, okay, at any instant. Okay, let's just at some random instant we have two trees connected ready with us. Okay, this we have done using find. Merge of x comma y is, let's say this is x, this is y. What you have to do is find the root or representative of x. Let's say this is a, this is b. What's the representative of x? Can I say a?
A. Yes.
What's the representative of y? Can I say b? It's b,
B.
right?
Yes.
So what you do in merge of x comma y is, given some random nodes, first you need to find what's the root or the representative of that particular two nodes. Okay, so in our case we got it as a or b. Okay, now you have couple of options, right? One of them being you can either connect like this, correct? And what would be my second option?
A to Y.
No,
Sorry.
it's always connecting the root nodes. Okay,
B to A.
exactly. So either it can be like connecting A to B or B to A, right? So these are the only possible options. Okay, and we will see which one is better to go ahead. Okay, so is merge of x comma y clear? Is concept
Mm,
clear to
Yeah.
everyone?
yeah.
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 Yeah, understood.
Okay, nice. Okay, so uh, now in order to decide, okay, which one needs to be connected to which one needs to be connected with another, there are two special techniques. Okay, so this technique is known as rank compression. Okay, rank compression. So there are two techniques. Okay, basically one is rank by height. I'll explain you what are this. Okay, rank by height. Another is rank by size. Right? And so going forward we will always be using this one itself, the second one, because this gives you kind of more power to solve other problems. Okay, so we will all, most of the times we'll go with this. I never used the first one. Okay, so I honestly used only this, and whatever the problems I have solved in DSU have made my job done. Okay, now so what we do is rank by size. Okay, so say we have something as some trees, something like this. Okay, let's say this is x, this is y. Okay, this is a, this is b, the same kind of setup. Okay, a is our representative, b is our representative. What do you mean by rank by size? Rank by size is nothing but the number of components available over here. How many node, I mean the number of nodes present over here. How many nodes are available in this a, I mean the number of nodes present in the representative in this one. It's 5,
Fine.
Five.
and here it's
Yeah.
2. Okay, so
Two.
what rank by size tells you is always connect the smaller one to the bigger one. Okay, always connect the smaller one to the bigger one. So in this case what we will do is just go ahead, attach this, that's all. Okay, so this is what rank by size. Okay, so whoever is having the more number of size, okay, please connect the smaller one to this, the larger one. Okay, so as soon as you connect, can you see something that now the parent of b is nothing but a. Initially parent of a was a, parent of b was b itself, right? But as soon as you connect b to a, the parent of b becomes a now. Okay, so is it clear? Is the rank by size clear?
Yes.
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 Straightforward, right? Just
Yeah.
take the larger one, smaller one को attach कर दो, खत्म. ठीक है?
Yeah.
Now, similarly, we do also have rank by height. Okay? Rank by height is nothing but whichever is having the largest height. Okay. Let's say we have some tree, something like this. We merged something, and it did form something like that, some structure. Let's say we want to connect this and this, okay, and A and B are again the representative. So what do you guys think? Which one is better? Is it better to connect B to A or A to B?
B to A.
Okay, and why is that?
Smaller size. With respect to say.
Size though this one, right? I mean,
Okay, with respect when it
Also,
comes to height,
yeah,
what is height? Difference between height and size, bro? Here.
this is the height, right? So see, if you connect A with B, what happens is it's kind of like it might increase the length, right? When you connect A with B, right? But if you connect in an opposite way, it will always ensure that you have the same size itself, okay? Because A ka maximum height was this itself, and when you connected a smaller one, the larger height remained same, right? So basically it's all about like whichever you are having smaller height, you again have to connect to the larger one. That's all. I mean, same as this, that whichever is having smaller size, you connect to the larger one. Similarly here too, we take the smaller height one and we connect it to the larger one. Okay, that's all. Okay, so is rank by height clear? And we wouldn't be using this, but just for a theoretical perspective, is it clear?
yes, bro.
Yeah,
Okay.
both are same, right? Small
Yeah.
to high.
Yeah, both are same. Correct.
Yeah.
Okay. Now, so let me tell you like why this is being used. Okay, rank by size. I mean, why it is being used most of the times. Okay. So what happens is when you so there is a theoretical paper. Obviously, I am not saying from my own words. So the max height of this, okay, whenever you merge from smaller to larger, the max height it can go is up to log n. Okay, so the max height can go up to log n itself. Now what happens when you do it, when you have only log n height, so can you see that you have to travel at most only for log n number of nodes? Let's say you have something like this, okay, some random structure. So what I'm claiming is that since the height can only be at max log n, the number of traversal at max traversal will only be log n. It cannot be more than that because any path will only have a length of log n itself, right? So can I say that only log n operation is needed to travel on this? Can I say that? Hana bolo, did you guys get it or not?
No, bro. Didn't.
No. What I'm saying is this is a theoretical research, okay? Whenever you connect these kind of like the smaller height to a larger height, the maximum length of the tree can only be log n, okay? The maximum length can only be till log n, okay?
Okay.
Now what I'm claiming is if you have to travel the tree, can I say, I mean between any 2 points or doing some manipulation, can I say the operation, the time would only take log n cost because you will only at max travel the
Yes, yes.
length of the longest, which is log n. So
Yeah.
does it make sense?
Yes. Bro, here n means the number of nodes in A plus B or only A?
In the entire tree, in this tree, whenever you merge.
Okay, after matching.
Yes.
Okay, okay.
Okay. So others clear? Sahas, Deva, Manan.
Yeah,
Yes.
yeah, bro.
Yeah.
Okay. So this is regarding the rank compression, which is rank by size. Okay. So the size can go till up to log n. So it's kind of useful for us to have this computation. Okay. Now, now. So this is regarding something as rank by compression. Okay. Now, so can you see that whenever we are merging something like this, right? So we are merging something with something. Now, let's say this is x. Again, this is a. What is find of x? What's find of x here in this? What it should written?
A.
A.
It should written a, right? So
Yeah.
let's say I am asking you multiple times that find of x, find of x, find of x. So what you need to do? You need to from x you need to go to its parent, From here you need to go to its parent. From here you need to go to its parent. Correct? It's the only way, right, for us, because just by traveling the parents we can kind of find the root. Correct? Now the
Yeah.
question for you
Yes.
guys is, what will be the worst time complexity for this? Given n nodes, what will be the worst time complexity to find the find of that node? Will it be log n? Will it be square root n? Will it be constant time? Will it be n?
Login.
Think of it again.
Maybe n, traveling all n nodes.
Yes. So see, what we were doing is, if the tree is something like this, then if I ask you every time for this, sh shouldn't you have to travel all the n nodes?
Yes, bro.
Right? So you have to travel all the n nodes in order to reach it. Now what I'm asking you guys, find of x multiple times, maybe like for up to 1e5 times. Okay, so every time you will travel this, and you will find it. So instead of that, can you think, instead of doing like this, since we have to return somehow a, how about this? It's a cool trick, right? That since, however, whenever I ask find of x, it will return a for sure. Instead of traveling continuously, why don't you directly connect this with this? Now if
Okay.
you call find of x, how much? It's just a constant time, right?
Yes, yes.
Right. So this is a technique which he came up with. This is known as path compression. Okay.
Okay.
That is, you have a path, but why do you just go on keep traveling to your parent? Instead of that, directly connect with your representative or the root node. Okay, this is known as path compression. Okay.
Okay, every node we should connect to A in this case.
Yes, so it's not like every time whenever we get a call of this, then only we do it. Okay, we just don't do it randomly. Whenever we get a call, we just go and connect it.
Okay.
Okay, now again, so can you see the worst case for this was big O of n? I mean, in the
Yes,
initial time we have seen it's big O of n, right? Now
yes.
again, it kind of gets compressed to log n again. Okay, I mean, although you can see this is kind of like constant time, but you still connect some other nodes also, right? Let's say there was this big tree and there was another big tree which came into picture. Okay, and suddenly you kind of attached this. Now again you have the max length of this, right? So it kind of like path compression is, it almost takes log n. Okay, but now you see we have two powers in our hand, right? One is path compression and one is rank compression. Okay, so if we do it together, if we use it together, okay, if we use it together at the same time, the time complexity for any of them, okay, for any of them, either the merge operation or the find operation. See, path compression is a technique which comes in what? Which comes in, whether it comes in find of x or merge of x.
Find,
Find, right?
find,
Yes.
Compression comes in merge, correct?
merge.
So whenever you use these two techniques, okay, at the same time, the time complexity becomes big O of alpha n. Okay, this is known as, it's very important to know, uh, inverse Ockman function. Okay, okay, and surprisingly, this is less than or equals to 6. 6 is the operation, okay, number of operation. So when you use these two techniques together, okay, the time complexity boils down to big O of alpha n, which is less than or equals to 6. So in our asymptotic case, it is as good as constant. Okay, and this is known as inverse Ockman function. Okay, so is it clear now?
Yes, bro.
Okay.
Yeah.
Yeah.
Okay, so this is the kind of theoretical perspective we have for the DSU. Okay, now let's see, like, whatever the question we are tackling, how can we solve it efficiently? Okay, so what we were given is something like this, right? 0, 1, 3, 2, 4. Let's say I ask you to attach uh, 1 and 3. Okay, what happens? Merge of 1 and 3, right? So what happens with merge of 1 and 3?
Both are having equal
Yeah,
nodes.
both are having
Mm,
a like kind of
mm,
equal size. Since the size is 1 1 initially, we can attach anything. Okay,
anything.
so पहले ऐसा रहेगा. The structure is like this. Okay, each one of them is a parent of itself. This is the starting initial setup of DSU. Okay, now can you see we have something like this after merging these two? Okay, no. Let's say I ask you to merge. Take some random. Tell me some random u comma v, anything. Shall we merge 2 4? अरे इसमें
Yeah.
Okay.
ठीक है. So let's say we merge 2 and 4 and I'm just randomly like making that. Since the size are equal, we are doing this. Okay, and now we have this. The important part is we were having initially how many components? Initial, in the initial setup, how many components were there in this phase?
6.
There are
6.
6, right? Correct. There are 6 components in total. Can you observe any pattern? The pattern is, if they are successfully being merged, can I say it is reducing by 1?
Yes.
If they are successfully
Yeah.
merged, can I say they are reducing it by 1? They are, right? They are.
Yes.
Now if you see again, we have successfully merged, and we have the, this is as 4. Okay, now let's say again some query comes in random and they ask you to connect maybe 1 and 4. Okay, now the important part, when you connect 1 and 4, or let's say 4 5. Okay, let's start with 4 5 first. When it comes to 4 5, what you need to do, you shouldn't connect 4 with 5, right? Rather you should find what's the representative or the root of 4, which is nothing but 2.
Mm.
What's the representative of 5? It's 5.
5.
The size of this is 2, correct? Because there are two components involved. The size of this is 1. So can I say, can I make this
Yes.
Yes.
right? So this happens now, and the size of 2 becomes 3. And since there is a successful merge, can you see the number of components are how many?
3.
3,
3.
right? And you see there are 3 components. Okay, and these are just very easy to maintain, right? As soon as the successful merge happens, we will kind of initialize a number and have it, right? And as soon as you are asked that, okay guys, tell me how many components are there, just return this and you're done. Just a single, like, one shot. So see how the power of DSU comes into the picture, that initially you were doing DFS, but now you see within a single click, I mean within a single shot, you're getting this number, right? So this is that powerful. Okay, now let's say again it comes and it asks you to maybe merge, I don't know, which one shall we take? Shall we take 3 2?
Yes.
Okay.
3 2. Yes.
Let's take 3 2. Okay, let's take 3 2. So 3 का क्या है representative? 1.
1.
2 का representative is 2. Okay,
2.
1 is having a size of 2. 2 is
2.
having a size of 3, right?
3.
So which one shall we merge?
1.
1 to 2.
हो गया.
1 to 2.
Yeah.
Okay, and if you carefully see what I mean, the structure is being maintained, right? and now the number of components get reduced to 2.
Yes.
Okay, now the
Yeah.
components get reduced to 2. Okay, so now let's say we have to merge 3 and 4 now. Let's say we have to merge 3 and 4 now. Okay, so there is this thing we will handle explicitly. So can you see now 3 and 4 are maintaining in the same component itself?
Yes.
Yeah.
Right. So when I say merge 3, 4, the representative of 3 is 2. The representative of 4 is also 2. Can I say if they are having the same values, that means they are in the same component?
Yeah.
So do nothing in that case. Because since however they are in a single component, if you cannot merge, right? Because they are already available in the single component itself. Correct. So in this case, we are not doing anything, we are just returning. And did you see that nothing got impacted? Our number of components are still 2. And see
Yes.
the number of components available here at 2. So that's good.
Yes.
So in that case, can we claim that we are on the right path? Right.
Yeah.
Okay. Now, and let's say finally something comes in, let's say 0 comes in and they ask you to please merge 0 and 5. So what we do is, okay, is it clear now? So at any instant of time, you see that you have this structure ready with you, okay, and you kind of immediately have the power to identify two important things: whether node U and V are connected or not. Correct? Can I say if the representative of both the nodes are same, they are connected?
Yes.
Yes, right? If both of them are having the same representative, can I say they are connected? I mean, you can travel from U to V somehow. We are talking obviously about
Yes.
disconnected graph only. So
Yes.
it's always possible, right? And second thing is, uh, can you can also kind of find out key how many components are available. Okay. So these are the
Yes.
two major two major techniques which comes in DSU. Okay. So if you are okay, so I mean if you are okay with the theory, probably we should go ahead and
Okay.
do the code of DSU.
Yeah. Yeah. Yeah.
Yeah, bro.
Sure. So is the technique clear? I mean, and I hope you
Yes.
have liked it. I mean, it's very powerful. This okay. So what we have is we have DSU stuff. Okay. Uh,
For every query, find the find function which will give the root.
no, no.
Merge.
First we are writing normal DSU code. ठीक है. उसके बाद वो क्वेश्चन करेंगे. Okay, so we have a class, okay, DSU. Now, what are the information we require? Can I say I require something as size to maintain size? ये वाला 2 का size 5 है. We need a size, right?
Every component size.
Yes.
Okay.
Hey guys, aren't you clear? Why do we require size? Deva,
Yeah. Yeah, yeah, clear, clear, clear.
Tas,
To know the whole components, right, in the particular tree.
size मतलब क्या है? Size of 2 is what? Size of 2 is what?
Two.
6.
6, right?
Okay, so 6. Yeah.
Yes.
Okay. And secondly, do we also need to maintain parent?
Yeah.
Okay. So since we will be given n nodes, okay, so we will maintain that. And
Parent is nothing but representative only, right?
no, parent is not representative. Parent is this. मतलब we saw, right, some structure. So if you this इसका parent ये है, this इसका parent ये है. Obviously, when you do path compression, it becomes like this. then the parent becomes this. But in general, the parent is, I mean, to whom it is connected to. Okay. Say you don't do path compression.
Okay.
In that case, it will be like this only, right? I mean, iska parent is not
Yes.
the representative, is this itself, right? So parent is
Yes.
to whoever it is connected to, directed edge.
Okay.
Okay. Now let's create a constructor, and what we will be given is n nodes, right? Since initially you know that all of the nodes are kind of disconnected together. Okay. So what we will do, this dot n equals to n. How many should I say this? Is it fine? Initially all of them are disconnected, so we have n components all together. Okay. Now size equals to, I'm just writing n plus 1 for safe side, because sometimes the question asks you from 1 to n rather than from 0 to n minus 1. Okay. Now we have to do some initial basic setup. Is it fine that initially all of them are having size as 1?
Yeah.
Yes.
And what will be this? Parent.
Itself.
So
Root.
like this.
Yes.
Yeah.
Same.
Yeah. Okay.
Yeah. Initial.
So we have something as what? The basic initial setup. Okay, that each one of them are having size as 1 and the parent as itself. Okay. Now there are two things, right? Public int. Can I say this? We need to kind of write this method find, which will give the representative.
Yes.
Yeah.
So it's again a recursive code. Okay. So if parent of x equals to x, what does this mean? Can anyone say this?
Single node.
No. It's a
It's
representative.
representative.
It's a root, right? Representative. Because if the parent of that node it's that node itself, can I say that is the point where we have to return,
Yeah.
right? Otherwise, see, this is what we have, right? A, B, C. What is the
Okay.
parent of C? Parent of C is C itself, right? So as soon as
Yes.
you hit this condition, can I say that I need to return C?
Yeah.
Okay. Now, when we are doing it for the A, okay, let's say there is one more node. Okay, let's say there is B also. Okay, let's say we are doing it for the D. When we are doing it for the D, however, we are trying to attach this with this, right? So can I say at the same time I can attach this with this and this with this also at the same time? Because why do again, you know, we we did not to wait for any query to come in and ask to connect. Okay. Instead, since however you are traveling in a recursive structure for the first time, as soon as you are doing that, why don't you attach it as you go ahead? Okay. So if parent of x equals to x, return x. Otherwise, int representative. Okay, what should I write here? Find of
Yes.
find of think and tell me. May I am at D. I am finding for this. This is nothing but to whom I should call.
The root.
And initial structure is like this, right?
We should call A in that case.
We
Mm.
should call A,
Yeah.
right? So A is what?
Parent of X.
Correct?
Yeah.
So if this is the case, once we are done, can I say this?
Mm.
Yeah.
Okay. Now what happens with this? Let's try to see in a recursive structure. Okay. This is, let's say, D, this is A, this is B, and this is C. When you call for D, it goes and calls for A. When you call for A, it goes and calls for B. When you call for B, it goes and asks for C. Since C is the base case, what we will do is we will return it C here.
Mm.
We will return
C.
C here. So we kind of got C now, right? But did you see we missed one thing? What did we miss? We are not attaching this still, right? We are not attaching this. Correct? This is still connected to A only, right?
Yes.
Whatever we got is C, but the parent link is still A. So instead of this, since we got C here, can I write now?
Yes.
Does it make sense?
Yes.
Manan, Deva,
Can you tell me again?
recursion clear hai?
Recursion is clear.
What does what does D will get?
A.
A. C. C आएगा ना?
C. Yeah, C आएगा.
D will get C, right? So
Correct.
we got C, but
Hmm.
if we have C, can't I just disconnect this parent link and attach it here?
Yes.
Value क्या आया? C आया. तो parent of D should be
Correct.
equals to C, and that's what I have written.
Correct.
Parent of
Hmm.
D equals to C.
Correct.
In fact,
Yeah.
if you see this, there is a very good observation that not only D got attached, can I say B and A also got attached if you see the code? Because
Yes.
this is the last line, right? So can I say that B का भी हो गया C से, A का भी हो गया C से, and this is also like this? Is it
Yes.
understandable?
Yes. Yeah.
Deva, are you clear? Or do you have some
Yeah.
please
Oh, got it, bro.
in case if you're not?
Got it. Got it.
Okay.
Yeah, got it.
ठीक है, is this clear? Fine. I hope you are clear with this. Okay. Now,
Yeah.
Yeah.
what we need is public right? Correct. We need merge function. So first thing, int x root. Can I say this? Key, you need to find the root of that.
Yeah.
We need to
Root of
find
5.
the root of y. Okay. If x root is equals to y root, what does this mean?
Same component.
Same.
If they are in the same, should we just return it because no point of doing anything, right?
Yeah.
Yes.
In that case, if it is not, we are size of x root is greater than or equals to if this is the case, can I say size of x root plus or equals to size of y root? Chota wala ko we connected with larger one. Since y root is smaller, I have connected with this. Does it make sense?
Yes.
Yes.
And finally, parent ka of y root,
Y
Equals
parent
to
of X root.
not parent,
X root.
x root, right?
Okay. 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 Yeah.
Else, just reverse it. Okay. So this should be what? This should be y
Y.
root. This should be x root. This should be x.
Yes, got it.
And once done, please go ahead. खत्म मतलब merge कर दिया ना, so you have successfully merged, right? So it should reduce, and if you see, this is the code for DSU. That's all, nothing else. Clear?
Yeah.
Okay, so this is what we have as a DSU structure. Okay, and let's try to tackle our initial problem and let's see. Okay, query on components. So is the code clear, others? I mean, Manan, Sam, Deva.
Yeah.
Yeah, understood.
Okay.
Yo.
अभी समझ जा रहे हो, कोड लिखना है कॉन्टेस्ट में, दैट्स द इम्पोर्टेंट पार्ट, राइट? Okay, so what shall we do? Quickly, let's initialize this. So we have these things. Okay, so we have number of nodes ready. Now we will use a DSU new DSU of n. Okay, so we have the things ready. Now we will be getting number of queries, right? And for each query, so what we are asked, either you should merge it or you should uh, find number of components, correct?
Hmm.
So int, let's say type. Okay, type means which type of query it is. If type equals to 1, that means what we are trying to do is
Find.
yeah, say find number of components. Okay, else connect two nodes. Okay, so in this case, can I say what? DSU of
Number of components.
exactly. In this case,
Merge of
okay, मैंने directly instead of writing here, is it fine, guys? Or
Yeah.
Manan, Deva, are you guys okay with
Yeah,
it?
yeah, yeah, yeah.
Yeah.
I just wrote it here, okay? Instead of int uv, I just wrote it here. Shall we run?
yes.
Yes, sir. चलो कितने nodes चाहिए? How many nodes? Shall we take this example itself?
Mm.
So there are 6 nodes, right?
Yes.
So let's say there are 6 nodes, and maybe how many queries?
3.
Let's go some more, 6 queries maybe. Okay, we'll try
Okay.
to see. Okay, so initially let's say we are trying to merge. Okay, so what we will do is, let's say type is 2. Okay, type 2 मतलब ये वाला, ये else case.
Mm.
And what we will do is we will try to merge two nodes. Okay, and what are the two nodes we merged initially?
1, 3.
Chalo. So nothing happens because we are just merging. Now we will ask for how many components are there. Okay, so we should get 5. And did we get 5?
Yes.
Yes, right? So it's kind of working. Let's see for others too. What do we merge now? 2 4 share.
Mm.
Yeah.
I am taking the type as 2 2 4. Okay, I am taking again the type as 2, and let's say we merge 4 5 now. Okay, okay, so if you see, we merged this thing. So how many components should be there now? Did we get 3?
Yes.
Yes.
Right, so it's kind of giving the perfect answer. And can you see like how fast we are getting? Matlab, this is what constant
Mm.
right? And let's, okay, I guess we are done. I mean, we have only one. ठीक है, कुछ तो लिख देंगे. I'm 2 1 and 5. I mean, it obviously done, but it kind of works. Okay, it gives you the perfect answer every time. Okay, so this is what DSU is. Okay, this is a very powerful tool, and it kind of help you in this kind of problems. Okay, so is it clear, everyone?
Yes. Yes.
Yes.
Yeah.
Yes.
Chalo, good to know. Now let's try to do a couple of problems on DSU. Okay, and then we will move to spanning tree. Okay, what should I ask?